this talk represents, let me say, I'm sort of part of the way through a journey, in that we used to mostly use non-informative priors, and this talk is all about weakly informative priors, although I think now I'm moving towards fully informative priors. So you're sort of catching me in the middle of this. And let me just give a little bit of background non-informative priors are sometimes a little bit controversial, and when I was a student, we were told there's no such thing as a non-informative prior because if you tried to use a uniform prior distribution, then it would depend on your parameterization. But that's sort of a little silly because there are certain parameterizations that make more sense than others. And when we wrote the first edition of our book, we had a lot of non-informative priors, and we just tried to make the point that non-informativity is not a pure mathematical property of a prior distribution. Non-informativity is relative to the likelihood. It's relative to the information you have in the data. So the fact that a non-informative prior depends on the parameterization, sort of okay. And so we didn't mind doing that. And at the same time, I think we are reacting against this attitude that Bayesianism is this subjective philosophy. And it's sort of like 20 or 25 years ago, I had this horrible time with these Bayesians because they would never want to check the fit of their models. And their principle was that our model is subjective and therefore it can't be checked. But if you think about that for a second, it's a little weird, right? Like, it just reflects my personal belief, so therefore I can't and shouldn't check it. Well, what kind of person doesn't go around checking their personal beliefs, right? A Bayesian, apparently, is what did that. And so I was really, resisted that. And I mean, even from a philosophical standpoint, the idea that you can intuit your posterior distribution, that your posterior distribution represents a personal belief is ridiculous. So, because if your posterior distribution, the idea is that your prior distribution is this unquestionable thing. You can't, you're going like that, like you can't hear me back there? Can you not hear me back there? Because I think everybody else back there can, so you could move up if you, wait, okay. Let's see, how's this? Is this a little better? Okay, thanks. Oh yeah, so imagine that as the philosophers used to say, that your prior distribution represented a personal belief which was unassailable because it was your personal belief. If that were truly true, if that were a really appropriate way of thinking, then you wouldn't ever need to do Bayesian inference. So you wouldn't need our book, for example, because you could just read the data and then intuit your posterior distribution. In fact, I used to say that you should be able to, if you really believed in subjective priors, you should be able to take the data and cut it. I hate this thing. You should be able to, is this work? Can you hear me now? Yeah, okay. So you should be able to take the data and, oh, excellent. Okay. You should be able to take the data and chop them into a fine paste and eat the data, and then you should be able to then process the data and then excrete your posterior distribution, and it should still be valid because it represents your subjective belief. So obviously that's not true. So in that sense, the idea of the subjective prior is really a way of enforcing consistency. It's not supposed to represent a way of being. So for all those reasons, we were really happy to use objective priors or non-informative priors. So over the years, I've come across situations where a little prior information will help. And so I gradually started to think that even though I didn't feel bad about using non-informative priors, I could do better. So that's what this talk is about. Now I'm going to start with two applied examples. So these two examples came up way before I thought about weakly informative priors as a systematic approach. These came back in the era when I was trying to do everything non-informatively, but sometimes I was forced to use an informative prior, even though I didn't really want to do it. Then more recently, we've been doing some work on default priors for logistic regression, hierarchical models, mixture models. And in these cases, that we realized that a little bit of prior information is a good thing. So first, my examples. This was a project we did, well, I guess 25 years ago. We were estimating, we were trying to estimate what would happen in an election if there was a shift in the vote towards the Democrats or the Republicans in the United States. And the question was, if the Democrats got more votes or fewer votes in the election, how many more seats or fewer seats would they receive in the legislature? So you can try to estimate that by looking at the distribution of votes. This is data from congressional elections in 1988. We're not showing the districts that were uncontested, which would be at 0 or 1. You can take this distribution and imagine shifting it to the left or to the right a bit to correspond to a shift towards one party or another in the vote. And if you imagine shifting all the histogram to the right a little bit, that would correspond to the Democrats getting more votes, and the difference in the area less to the right of 0.5 would correspond to the extra seats that the Democrats would get. But when we were doing this, we realized that there's variation from election to election. We didn't really want to just shift the distribution over. We wanted to actually estimate the underlying position of where each district would be. So basically, we wanted to do is partially pool each district. It's hard to, I can't reach. I guess I can, no, this is sort of pointless. We wanted to pool these towards this mode and pool these towards this mode, and maybe pool things in the middle sort of partially towards one mode or the other. So the background of this problem from a technical standpoint is that we wanted to estimate varying parameter for each district based on one data point. We wanted to partially pool towards the mean of the distribution, but because it's a mixture, we want to partially pool the Democrats to the mean of the Democrats and the Republicans to the mean of the Republicans. If you were to just sort of push a button and do a standard hierarchical model, you'd pool everything towards the middle, which wouldn't make sense. So we wanted to fit a mixture model to these data, but if you just sort of fit a mixture model with maximum likelihood, it blows up. Because there's a degenerate result when one of the mixture components has 0 variance. It has an infinite likelihood. Not only does it have an infinite likelihood, but the integral of the likelihood near that area also is infinity, which means a flat prior Bayesian analysis blows up also. So we used informative priors. We centered one mixture component at -0.1. Well, I should say at 0.4. This is relative, sorry, we did everything relative to 50-50. So we have one mode for the Republicans centered at -0.1 with a certain standard deviation, and then a mode for the Democrats centered at +0.1. And then we have a third mode to capture all the crap that's not in the first two modes, because a mixture of two normals doesn't seem to fit quite well. And so we basically held the hand of the model. We held its hand. We also gave it a prior for the height of the modes. And then it fit the data pretty well. Not just this one data set. We used the same model for many elections. And the way I think about this is that there's a model we wanted to fit, which was the class of mixture models that sort of looks vaguely like this, which is smaller than the class of all mixture models, which includes all sorts of things that we didn't want. So we used the prior to control the inference. It's not a matter of saying we have a subjective belief that a certain parameter is a certain value. It's just that we needed the inference to be stable. I'll go on to the next example. So the next example was a toxicology example in which we had a parameter having to do with how a toxin was dispersed in the body, and we knew very little about it. My colleague had a prior estimate based on the literature that it was around 16. But he thought he could easily be off by a factor of 10 or a factor of 100. So you see that log 10 on the log scale, the standard deviation. Very little information. But we had data on 6 people. So, of course, you could take the 6 people and say that each one has this vague prior, but we actually could do better with a hierarchical prior. What we said was that we don't know much about this parameter, but we do know is that people are similar to each other. So I think all 6 people, let's say this range is the range of the prior distribution. I think all 6 people might be here, or they might all be here, or they might all be here, they might all be here, they might all be here. I don't know where they are, but I think they're close to each other. So I said a hierarchical prior where the 6 people have a common mean with a small variance. They're close to each other, factor of 2. But I don't know where the mean is. So this was a weakly informative prior. I mean, I'm able to specify a certain amount of information. The reason this works, and the common thread for all these examples, is that we have numbers here. It's not epsilon or alpha. It's a number like 10 or 2. That's what characterizes a weakly informative prior is a number like 2 or 10. So if you see 1,000, that's not a weakly informative prior. That's a non-informative prior that for some convenient reason you've set to 1,000. If you see a number like 0.001, that's a non-informative prior. If you see lambda, that means you haven't specified the model yet. So you need to put the prior in lambda. But if you see a number like 2 or 10, that's weakly informative. Now, obviously, to do this, you have to know what 2 or 10 mean. You have to have a scale for things. I'm willing to pay that price of knowing what the scale of the problems I'm working on is. So one way of saying it is that I think we should be using weakly informative priors instead of using non-informative priors, instead of using informative priors, and I'll argue why I think that. Another way of saying that is that weakly informative priors are what we already use. So this is sort of a traditional Bayesian argument. We're all doing it. So everyone's regularizing. You can never be fully non-informative. And even if you think you're being fully informative, you're not really, because there's information that you're not using. I think just to sort of step back, the role of the prior distribution, sometimes we call it a placeholder. So you use a prior distribution, but you're willing to go back and add more information later. So perhaps prior isn't the best term. Perhaps external information is a better term. I use my external information, then if I need to, I gather more. Of course, the model, the statistical model itself is a placeholder. So a very common example in applied statistics is we model some regression, and some of the predictors are measured with error. But usually we don't worry about that. Sometimes it creates a problem, and we go back and we fit a measurement error model. Our original model was a placeholder, right? This is what we do all the time. We always go back and elaborate, so there's nothing special about the prior there. As the song goes, that life is what happens while you're busy making other plans. So we're busy making inferences given the models that we have. Knowing at some point we'll go back and improve our model, or maybe we won't, because maybe we have better things to do. A theme I'm going to also come back to today is that the prior that you use when you're doing full Bayes is not necessarily the prior you're using when you do Bayesian point estimates. I think this is very important for this crowd because a lot of you all like to work on big problems where you need scalable methods, and you use methods like EP and VB. And it turns out that the prior that you might use to get a good, well-performing VB estimate is not necessarily the prior that you'd use if you were doing full Bayes. And we tend not to think about that. We tend just to think the model is the model, but the model is really defined relative to how you're going to summarize the inferences. Okay. So I'll start with a simple example. You've heard of this one, I think, this model. I think it's called a one-stage neural network in AI. Is that right? I can't remember what a shallow net, maybe we call it. Here's some data. This is the best kind of data, simulated data, and from the model, there it is. That's great. Here's some more simulated data, and this is wonderful because you can get perfect prediction on the training set But we have a horrible feeling that we might be a little bit overconfident when new data come around. And this isn't good, so we call this separation. This happens. Here's an example. It happened to me. This is what we call a quasi-real example. I was really writing a homework problem with real data, and this happened. So the example was you're predicting whether someone votes for the Republican in the presidential election as a function of their sex, their ethnicity, and their income. It's about 1,500 people in each year. Here's 1960. So in 1960, while women were slightly more likely to vote Republican than men, controlling for the other things, it's not quite statistically significant. Blacks were more likely to vote for the Democrat. Richer people were slightly more likely to vote for the Republican. Here's 1964. Women slightly, well, it's close to zero. Look at the coefficient for blacks. So blacks are much less likely to vote for the Republican in 1964. This coefficient is pretty big, though. You don't usually see logistic regression coefficients so big. I didn't really know how to interpret it because the standard error is 420. That's, well, of course, if we had run this regression a little longer, it would have converged to minus infinity, that there's complete separation in the data. In that survey, there are 100 black people in the sample, and none of them said that they would vote for the Republican who was opposed the Civil Rights Act. Now, I don't think the true coefficient is minus infinity. There actually were black Americans, African Americans in 1964 who voted for the Republican. None of them happened to show up in the survey. Now, one thing I have to remind you all is the goal of the survey is not to learn about the sample, it's to learn about the population. Because sometimes people have this worship of data, but like your goal is not to fit the data. The data means to an end, right? The goal is to estimate the population. This is not a good estimate. If you go back 1968, 1972, things are fine, but logistic regression is failing here. If you look at the left column here, it's these are the regression coefficients for the coefficient for black. This is the I fit the model separately to data from 1952, 1956, 1960. Here's 1964 with the infinite standard error, 1968. And you see that there seems to have been a regime change after 1964 with African Americans supporting the Republicans less. There's another regime change in 2008. The data here don't go that far. Just as sort of a control case, I'm showing you the estimates and standard errors for the coefficient for income. Now, then I put in my weekly informative prior, and I'll talk a little bit about where it came from. But when I do this, here's my estimates. It doesn't do anything except in 1964. And in 1964, it does what looks to me to be the right thing. The estimate for this year is lower than all the other years, but it's not too extreme, and it has a big standard error. It doesn't do anything to the coefficient of income because we have a lot of data. There are different flavors of the prior. You could use a Cauchy, a T, a normal. It doesn't really matter that much, slight differences, but not much different. Now, this is my default. So I sort of like this example. Obviously, I like it because I'm presenting it to you. We use our default prior. It's not a prior that we believe. I'll talk more about that in a moment. But it gives a reasonable answer on this problem. Now, it's sort of cheating because we maybe developed our default prior partly from examples like this. But still, it's sort of good. Now, the default prior here is centered at 0. Sort of it has to be because it's the default. But you know, even before gathering any data in 1964, you probably would have guessed the coefficient would be negative. So it's not, the default prior doesn't represent the correct prior. It doesn't represent your actual knowledge. But it represents a little bit of knowledge that regularizes the solution. And this is what it's all about. It's about regularizing. So we use less knowledge than we actually have, but enough to give a stable answer. And I think this was what was sort of counterintuitive to me. Is that this is what we used to say this in New York, that like you could spend a lot of money and live, and you could either spend a lot of money or you could live in a dangerous neighborhood, right? And the question was, is there an overlap? Like, and the story was no. Like, you could, like, even if you spend a lot of money, you're still in a dangerous neighborhood. You can't sort of get what you want. And here, the analogy here is, like, there's sort of two things you can do. You want regularization. But to get regularization, you have to sort of spend. You have to put in information. And the interesting thing here is that you can put in a little of information and get useful regularization. That's the important concept, that we can put in information that's pretty much uncontroversial and still get a real benefit. And if you look at what people do in Bayesian inference, they're quite commonly using very, very weak priors, 10 to the minus, numbers like 10, like 1,000, 10 to the 6th, things like that floating around, because they're sort of so afraid of putting in any information at all. And it turns out if you put in a little bit, you can get a lot out of it. Now, what is the prior here? So I told you about separation. My prior information is that logistic regression coefficients are almost always between -5 and 5. So remember, 5, that's a number. So that's, now I don't think 5 is some absolute truth. If I was Bart Simpson, I'm sure I would say 4. But it's not that different between 4 and 5. How do I think about 5? Well, on the logit scale, 5 takes you from 1% to 50% or 50% to 99%. Now, just to calibrate this, the lifetime risk of dying of lung cancer if you're a non-smoking man in the United States is 1%. Surprisingly high, perhaps. That's what it is. It's 50% if you're a heavy smoker. So the effect of smoking is 5 on the logit scale. Now, there's a principle of epidemiology. Everyone knows that smoking is the most dangerous thing out there. But there's actually a principle of epidemiology that for any risk X, the interaction between X and smoking is larger than the effect of X itself. There's anything that's bad for you, it's more bad for smokers than non-smokers by more than the main effect. So now let's sort of work through this, okay? The effect of smoking is 5 on the logit scale. Smoking has a larger effect than anything else. Therefore, all effects are less than or equal to 5. So we can, that's prior information. Well, so I'll put this Cauchy. So I don't want to just do a hard constraint at 5, because of course not only are things are more likely to be small than, not only are effects not as large as 5, they're also more likely to be small than large. And I'm putting this Cauchy thing in because I feel like, well, I want a flat tail just in case there's something going on. So that's our default. In order to have a regression coefficient, you really have to have the model on x beta, not on beta itself. Because beta doesn't mean anything before you multiply it by x. So I'm assuming that the predictors have been rescaled in a reasonable way. And this is sort of obsolete here because we did this implementation using EM, which was sort of clever and ugly at the same time. But now we do it directly in Stan, so it makes life easier. We did a little cross-validation study on a corpus, and on the high numbers are bad because it's predictive loss. Our best prior in terms of minimizing predictive loss was a Cauchy, among all T families, was a Cauchy with scale 0.8. So we actually use a Cauchy. We're recommending a Cauchy with scale 2.5, which sounds like the wrong thing to do. And this gets back to this idea of weak informativity. That somehow I still have this residual training where I feel bad about using prior information. So I guess I'm still recommending that we use something that's not the best performing prior because I still feel a little guilty about using prior information. So that's what I was doing. Okay, now at this point you might reasonably ask, why should you care about this? Because I'm giving you these like little problems with 3 predictors and 200 data points, and you might feel that you don't have to worry about this. You might feel that for one of 2 reasons. One, you might feel you have huge data sets, so you're not going to have separation. The other is you might feel that you don't need priors because you can auto-tune everything using some sort of cross-validation procedure. And so let me talk about that. So First is we have our data are sparse. When although we might have data sets with hundreds of thousands or millions or even zillions of data points, we're also asking lots of questions. And we ultimately want to drill down and ask local questions for which our data are sparse. One way I like to say this is that big data need big model. Because big data are data that are scraped or come for free in some way. Big data are typically not simple random samples of a population. So when we want to learn about a population from some big data, we typically have to do a lot of adjustment to map the sample to the population. So some sort of statistical modeling is going to be needed. And when we do that, we're going to find that we have sparseness, and we are going to come into situations where prior information is relevant. In fact, even if we try to estimate all our tuning parameters using cross-validation, that's not going to solve the problem. Because if we have small numbers of replication, then the cross-validation itself will be noisy, and it comes back to the problem of priors. Here's another example. This was an example from an old statistics article, not by me, by about 30 years ago, demonstrating the use of Bayesian statistics. This was a simple pharmacology example with some drug that they were testing on rats. The doses on the log scale, which is why you have negative doses. At low dose, no rats were dying. At high dose, all the rats were dying. And so they fit a logistic regression and got the estimate and the standard error. I was curious about this, so I threw our default prior on it and got this. Well, this makes sense, right? Because remember, it's supposed to be less than 5. So, I mean, how bad could this drug be? It can't be as bad as cigarette smoking, right? I mean, let's be realistic here. But this is sort of fun. I was actually surprised because when I did this example, I was expecting the prior wasn't going to matter, and that this was going to simply just show, oh yeah, we have data. We have data. You don't need the prior. Actually, the data aren't so strong. So I want to show this picture. It's sort of funny. There's the data. 0 out of 5, 1 out of 5, 3 out of 5, 5 out of 5 are dying. Here's the fit, and here's the posterior mode that we got from the Bayesian approach. And it seems a little upsetting, like, well, of course, we know that we're not getting the maximum likelihood estimate, but to actually see this, like, we're really, like, going against the data. But to understand this, you have to realize that with only 5 points, 5 rats per data point, the error on each of these points is on the order of 1 over square root of 5, which is about 0.2. So if you think each of these points could be 0.2 higher or lower, then you see that a lot of curves could go through these points. Now, what are you going to believe? What are you going to use? It depends. And I think, well, I wrote this that sometimes in statistics, the maximum likelihood estimate is considered to be sort of conservative thing to do, like the safe thing to do, although it depends on the context. In this case, I feel that the maximum likelihood estimate is being jerked around by the data. And if you're really dealing with samples of size 20 and you're trying to estimate effects, then I actually would prefer to take the Bayesian estimate. Now, really, what I'd really prefer is to use an actual prior based on other old drugs that they've tried. There's no need to use the default prior. You should be able to do better. But if I had to use a default, I think I would prefer the red curve to the blue curve. Before I go on to the next, I want to talk about some other models. But first, I want to tell you a sort of embarrassing story. So it's something that happened to me this morning, and it makes me look pretty stupid. And I think at this point, you can take this in 2 ways. So one is an irritation that you woke up, earlier than 9 in the morning to hear a stupid person talk to you for an hour, talk at you for an hour. But I want to flip it around, give you the positive view. And the positive view is that, like, even though I'm sort of an idiot and missed this obvious point, I've still been able to make contributions to statistics. So I think it should be inspiring that a stupid person can do so much. I think you should feel that you should feel inspired by that and think of how much more you should be able to do. And so, okay, so what happened was I was fitting some logistic regression model. Someone wanted to fit a robot model. A robot model is a logit model, but instead of a logistic link, you use a T-link, so it's more robust. So he said he wanted to fit it, and they had some programs. Said, oh, let's just fit it in Stan. It's really easy. So I wrote the Stan program, and we fit it, and that was fine. I fit it, and that was fine. But then I was worried because I think, well, sometimes you get data with separation. So I thought I would demonstrate what happens if you throw a prior on. So I just did this. I went back to the logistic regression, and I just programmed up this model. I mean, the model that I've been talking about over and over again here for the last 15 minutes. I just programmed it up in Stan with a Cauchy prior, and I created some fake data. I can show you, like the here. Of course, you can't read this, but that's not the point, is it? Okay. I just wanted to show you that I did this. So I simulated some R code. I simulated some fake data, 100 data points with 2 predictors, and I did this thing where I set the data to 1 whenever one of the predictors was 1 to create separation. Then I started fitting the model, and I fit it with GLM, which if we can find it somewhere, well, we'll never be able to find it. I fit it with GLM, and you get it blowing up. Believe me, it blows up. And then I did the Cauchy prior, and I got this result. So it's impossible to read this also, but I did this. I'll just tell you, I used the Cauchy prior, and everything was supposed to be so well behaved because I wrote a whole paper about this. It was accepted. 3 referees thought this was fine, and it was accepted in a top journal, and it's been cited, in the high 2 figures. And I did it, and it's like I was getting this blowing up. Like my estimate, you can't see this, but this regression coefficient is 17.5, this logistic regression coefficient, for this thing with 100 data points. It's not supposed to be that way. I did this so recently, I didn't have time to make a slide on this. That's how recent it was. So I was like, what is going on? So I stepped back, and I used a T with 4 degrees of freedom, and it was stable. So that was like, okay, fine. It's Cauchy. Who wants to use a Cauchy anyway, right? But then I was like, but what's wrong? What about that paper? And then okay. So then I went back, and well, Stan, of course, can fit maximum likelihood or posterior mode too. Is Stan, right? So I refit the model. This is sort of ugly. I haven't cleaned up the output, but I got an estimate, and now the coefficient estimate is no longer 38 or whatever it was. It's 3.6 with a standard error of 1.7. You people in the back, you can just ask your friends in the front, and they'll be like, yeah, that's what it says. Okay. It's the same model. It's the Cauchy model. Right? So what's going on? Well, I realized what was going on. So I'm not a complete idiot because I realized it. It just took me I had to do that simulation to tell. Wait, now I have to get this out of here so you can see the slides again. Okay. Okay, so this is what happened, is that if your goal is to find the mode, the Cauchy is just fine. But if you're doing full posterior, the Cauchy has this big tail. So if you have a Cauchy tail, and then you have complete separation in the data, which means you have a flat likelihood, then that means your posterior has this Cauchy tail, which means your posterior has no moments. Well, it's a 0th moment, but nothing much after that. It doesn't have a mean. It doesn't have a variance. It includes all sorts of things you don't want. It's not regularizing enough. So if you're going to do full Bayes, the Cauchy isn't a good prior there. It doesn't do enough regularization. If you're going to do the mode, it would be okay. The prior, that's the right thing. So actually, I think I would no longer recommend the Cauchy even for mode finding, because what's the point of having this prior around the thing you have to throw away later? I was only using the Cauchy for some convenience. But it's an interesting point, and it comes up a lot, that you don't need as much information to regularize the mode as you do to regularize the whole distribution. Which is fair enough, but as I said, I didn't think about it. Like I had a prior that worked, and then I thought I would go from there. It's actually not uncommon those of you who've done Bayesian inference, it's not uncommon to have a model where maximum likelihood is okay, you do a little regularization, it's okay, but then you do full Bayes thinking it's going to be bad, and it's worse. And this is sort of what's going on. It's like it's not regularizing enough for full Bayes. Now this is doing some weird thing. We'd have to then, sorry. Okay. Okay, next problem, hierarchical variance parameters. So this was a problem. I had a hierarchical variance parameter sigma. This is the marginal likelihood, the posterior density under a flat prior. The best estimate, the posterior mode is 0. But 0 isn't a good estimate, right? Because it's on the edge of parameter space. So this comes up sometimes in the posterior when the mode of the distribution's on the edge of the boundary. What do? You can't use the mode. Well, if I did full Bayes, it wouldn't be a problem maybe, but we're often actually are doing mode-based computations. Again, you people in this room, you're so scalable. You know about sometimes we have to compute the mode. We can't do the whole distribution. So we need to have statistical methods that work well there. So what I want a weakly informative prior that controls that. There are certain things that were floating around in the literature, like uniform distributions, inverse gamma distributions. Now, I propose this half Cauchy distribution. Now, of course, I'm already hating this Cauchy thing, but this is what's in the literature, so I guess I have to stick with it. The half Cauchy distribution, in this case, it's a Cauchy with a mode at 0. It's not quite as bad as in the previous situation because the likelihood tails down here. So the long, is this going to work? Does this work? Can you hear me? Okay, thanks. Okay, I think for the benefit of those in the back, I'm going to start over now. So there's this thing, the half Cauchy performs very well near the origin, but does not lead to dramatic compromises in other parts of the parameter space. So the issue is that the prior is sort of reasonable or helpful with respect to the likelihood that you have, which is sort of always going to be the case, really, that it's always relative to the likelihood. Here's an example. This is what people have been doing before. So I have my likelihood. Here's the flat prior. People had been suggesting inverse gamma prior distributions in the literature. Somehow the inverse gamma with degrees of freedom 0.001 was considered to be very non-informative. But as you see, this is the likelihood. These are simulations from the posterior under a uniform prior. And this is what things look like with these inverse gamma. So this so-called non-informative inverse gamma prior is actually extremely strong relative to this likelihood. It gives you huge amounts of information. And of course, if you decided to make it weaker by making it 0.0001, it would make it even stronger. So what's going on here? How is it that this prior that people thought was weak is really strong? Is that this strength of a prior, again, it's relative to the questions that you're asking, and it's relative to the likelihood. And in this situation, making this 0.001 is making it stronger and stronger and stronger. So this gets back to this idea that you can't really avoid parameterizing a problem. Now, the uniform prior itself had problems when the degrees of freedom in the data were small. We had a very long tail on the posterior, and this half Cauchy shrunk down, cut off the tail much better. So it worked well. Again, I don't really believe the Cauchy, and in other situations I didn't really like it, but here it worked pretty well because there was enough falling off in the likelihood that we got the behavior that we wanted. And again, this is a real problem, okay? So something that we do all the time, and I know you do also, is we set tuning parameters. So I'm trying to speak your language. Like I say, we have hierarchical models, and we have hyperparameters that are hard to estimate. The data are weak. You might say you have tuning parameters that you tune using cross-validation. Now, cross-validation is a complete snare. I mean, it's great, but it fools people. Because cross-validation, like usually people do it and they don't get a standard error, people have this way of thinking that the cross-validation estimate is correct. Like, after all, this is the tuning parameter that optimizes the cross-validation error. So it has to be correct because it optimizes the cross-validation error. And then our objective function was the cross-validation error, and we've optimized it. So therefore, we're fine. Okay, no, but really, what you're doing is, let's face it, you're estimating. You're not tuning something. You're estimating a hyperparameter, and you often don't at the top of the pile. You don't have that much information about these things. And one thing I've been learning over the years is that we have less information about the hyperparameters than we realize in the data. We have more prior information about the hyperparameters than we realize. So we'll often get these really long tails, even though we know that certain values don't make any sense. So really what I think is we should be using stronger information. If you're cross-validating, then you should be cross-validating some penalized function. You should be using a soft constraint to get estimates that are reasonable. And this is a weak prior, but it's a start in that direction. Now that was full Bayes. Now I have point estimation. And I mentioned this earlier that if you're doing inference for hierarchical models, you can get a boundary estimate, which isn't so good. Before going on, I just wanted to say that I think of point estimates as an approximation to the posterior, and you probably do too. In the statistics world, in the applied world, there are a lot of people who just want point estimates, who just don't want posterior distributions. I mean, in any case, these boundary estimates aren't so good. Remember this. I don't like this thing. And maybe this is pretty. What I did here is I simulated fake data. And for each fake data set from a hierarchical model, for each fake data set, I drew this curve, which is the marginal likelihood of the hypervariance. And here they are. So this is 100 different curves. This is 1,000 different curves. And it's pretty, okay? But you see a lot of them have a peak of 0. So in this simulation, I think the true value of the hyperparameter was 0.5. And in half the simulations, the point estimate was 0. So it happens, right? And it has real consequences because you get a point estimate of 0 and you're saying there's 0 variation. And for some settings that can make sense because it means the variation is so small it's undetectable. But other settings in a predictive context, when you have 0 variation, you're shrinking everything and all your predictions for all the units are identical and you don't want to do that. So I wanted a non-zero estimate. I'll skip this slide. I wanted a bunch of things. So I wanted the point estimate to never be 0 because I don't want a boundary estimate. But I don't want the estimate to have a lower bound. Okay, now by that I mean if I were to suppose I were to take a likelihood like this and give it like a log normal prior. Well, log normal prior essentially has a lower bound. It cuts off near 0, which means that if the data are small enough, your estimate won't respect the data. So I wanted the estimate to be data respecting and not have a lower bound, respecting the likelihood. I wanted it to have statistical properties like bias and variance that were comparable as good as the maximum likelihood estimate because I want people who care about that to use it. I wanted it to be easy to compute, and I wanted it to have a baked-in interpretation. So this is like, Arrow's theorem, like you can't have it all, right? Like, like you can't have all the traits that you want in an estimator that you want to marry. You have to sort of settle for certain things. You have to accept that maybe she's not everything that you want, but she has certain properties that are optimal. And so, as long as she's on the efficient frontier and, works with your particular loss function, then you can maybe accept that will, that will satisfy your criteria, and you can, use this estimator in your future work, right? So it's like you might think, what do we have to give up? Now, the amazing thing, though, is just as in a Disney movie, actually, we were able to satisfy all these properties and find our true love of an estimator that did all of it, sort of amazingly enough. And it's just this, well, this gamma 2 infinity prior. It's a prior that goes like this. And you see the likelihood in the posterior. So what it's doing is it hits 0, so it can't have a mode at 0. But it's going up linearly, which means as close as the likelihood is to 0, you'll always, if the likelihood is very close to 0, then the posterior will be close to 0 also. It doesn't cut off near there. Now, it's surprising. Like, it took us a while to find this because people are used to using an inverse gamma. An inverse gamma cuts off near 0 and has all these problems. A gamma doesn't do this. On the other hand, if you're doing full Bayes, you don't really want to cut off near 0, maybe. So it depends on your purposes. But this made me very happy. You just slap this down and you get reasonable answers. You get it. So this is really great. I mean, it's somehow less. And I think this is going to be very important for when we're doing things like setting tuning parameters using cross-validation in complicated models. Because sometimes it turns out that the best thing to do is complete pooling and set tuning parameters to 0. But there are situations where we don't want to set things to 0, even though they happen to win in the data set. And this is a very simple idea that allows us to do that. Now, I have more examples, but not really time to show them all. Oh, sorry, I should say, beyond this, you can sort of show mathematically that when the posterior mode is 0, that you're basically shifting things over by one standard error. And the graph on the right shows that you can also have the prior can eventually go back down to 0. If you use a proper prior, then, but it doesn't really matter too much when the estimate's close to 0. For full Bayes, it matters. So I would say probably I'd prefer to use the proper prior, because for full Bayes, the proper prior will work. And for point estimation, it doesn't really matter. It's not really hurting you. You can do something similar with correlation parameters. So it turns out if you estimate varying intercept, varying slope models, that it's quite common to get estimates that are on the boundary. So if you've ever done this, if you've ever estimated a covariance function, a covariance matrix of indirectly observed data, if you've ever done this, like you're estimating a covariance matrix, and you don't have the data observed directly, it's like a varying slope, varying intercept model. It's quite common to get correlation estimates of +1 or -1. These are just meaningless. They really degrade our inferences. It's very hard to report numbers that I don't believe. So in this case, you're getting modes of the correlations of +or -1. But instead, we can use this beta 2 prior. Do I have a picture? I don't have a picture. Like this. That's just 0 at the boundaries, and it works just fine. Again, if you're doing full Bayes, you don't really need it, but for this point estimation, which is a big game that people play, it's helpful. Now, you can also, we can set this up more generally using this Wishart prior. So again, it's this funny thing that people usually, the inverse Wishart is conjugate, but it turns out the Wishart does what you want. It's just sort of a funny story. This is connected to some other things I don't have time to talk to you about. Okay, mixture models. I have stuff about mixture models, but I won't talk about that either. Well, I'll tell you briefly. Suppose I have a mixture model with like 12 components. And you know the problem with mixture models, estimating them, is that you can get components with really small variances. That's what makes things blow up. So what I'll do is I'll make a hierarchical model where the different variances themselves come from a common distribution. So I think that, and that's sort of related to these Dirichlet processes, things that people are doing. Again, so you set it up hierarchically, and it will work better. Okay, now, is there general theory for weakly informative priors? The answer is there is some general theory, but it's really under development. So one idea is you set up, you talk about there being a true prior distribution, which represents the distribution of parameters and all the problems you might analyze. And then you have a subjective prior, which represents your prior information. There's this intuition. Well, it doesn't have to be normal, but of course we'll start with our theory in the simplest example, because if once we get it working, we can think more generally. Right? So the idea would be the weakly informative prior, you take your subjective prior distribution and spread it out. And there's some trade-offs, right? So it works like this. If kappa, if you might be wrong, the idea is that if you set the prior to be broader, you do less regularization, but you're less likely to cut off something important. And so there's some intuition that it makes sense to be a little weaker than you think, because the loss, it's like worse to remove something that should be there than to just not regularize enough. And I have this intuition that there's some theory that under reasonable conditions, like k equals 2 might be good. But I don't really know. I've had great difficulty trying to prove anything about this or really formulate it well. Now, there's another idea. This is a new paper by a bunch of Norwegians that.
And an Australian.
And well, a bunch of people in Norway. And they have this idea, it's very clever, and the point is, to specify weakly informative priors, you have to add something, right? So I tell you have to put a number in, like 5 or whatever. So their idea is that if you have a model and you want to put a prior distribution, you need something extra. You need a base model. So you have some model P of theta, which is like, the model, we need a prior on theta. But what we're going to define it, we're going to have some base model. Simple would be like theta equals 0, right? So some model that you're defining things relative to. And they set up what they call a penalized complexity prior, which basically means that prior distributions close to the base model get more weight, and further away from the base model get less weight. And one thing I like about their approach is that they have user-defined scaling, so they say that the user still has to specify a number, which is how close are things to the base model. And so I think this is a very interesting idea, and I think this might be a useful way of proceeding. Because again, the challenge of weakly informative priors is like it's weakly informative relative to what? You need to specify the information. Okay, what have we learned today? Most importantly, you know this, but it's not in your textbooks exactly. It's not in your theory. And that is that models need structure, but not too much structure. It's very tricky, right? If you put too much in your model, then you're not listening to the data. But if your model is too plain and doesn't do enough regularization, you can't hear the data either. But regularization is so crucial to what we do, but regularization is typically presented as a way of dealing with problems. Even I did that today, right? It's like, oh, we want to do something simple, maximum likelihood, whatever. We can't. We have to regularize it. What a pain. But we can't really think about that. It's really that a model is a way. I mean, why do we need models at all? Why can't we just look at the data? We need models because we need to structure our analysis of the data. There are too many things the data can be doing. Models convey a lot of information. But as Bayesians know, the values of the parameter in a model also convey information. It's artificial to put all the information in the structure of the model and none of the information into the parameters themselves. I talked about this. I didn't really talk about this today, so I'll skip this. Prior distributions that work well for full Bayes are not necessarily what works well for point estimation and vice versa. And finally, I think there should be a way of formalizing the losses that occur when we put in too much prior information and not enough prior information. And I would say our existing theoretical framework is not quite enough yet to handle this. We probably have to broaden our theory to catch up with practice. I hope this was helpful to you.
So one thing I think is kind of interesting with the approach of statisticians versus people in, say, AI or machine learning is when you talk about priors, you sort of you didn't spend much time talking about the logistic regression as the model for the nice example with the voting. And it's almost like you take that model as a given because I guess it's been used in the literature or you expect frequentists have used it and looked at those parameters. And so there you want to apply a prior distribution over those parameters to make inferences. So for example, why not change the link function? So if you use a probit link function, then the implications of your prior are very different. And there's a range of different link functions you could do. I think it's just the type of questions we're answering, that different approach. But I think my tendency in machine learning is to try and not talk about priors, talk about the model as a whole. And I wonder if you had any thoughts on that.
Oh, I completely agree, and I'm always saying that, so I'm a little embarrassed that I didn't say that here. So I think you're right. We could talk about weakly informative models. That would be a better way of saying that. Right.
I want to thank Andrew Gelman for his lecture again, and just, yeah, it was great. Thank you.